Hello teacher and welcome to my presentation. And now I'm going to talk about my project. It's the reinforcement learning project, and my topic is applied q-learning and essays, essays as SAR algorithms on cliff walking gym environment. And my name is Pham. I'm from the AI and robots major. So in here, today we're gonna talk about the introduction and methods, and I introduce methods that I apply in the projects, and next we do experience in projects, and we have some conclusions in our project. So let's move on to discuss on the environment. So it is a gym environment clips working. It's, as you can see in the picture here, and the product is the box is 4 multiplied by 12 matrix with using a number matrix indexing. So it's the in the point 0 in the point first 3 zeros and a start bottom, as you can see here, and the first and 11 as the wall at the bottom right, and the third and the 3 1 to 10 as the cliff at the bottom center. Its actions of the environment, and action of the engine here is a forward degree action deterministic action. Is the first one with 0 index is move up, 1 is move right, 2 is move down, and 4 is move left. And the observation here is there are 36 and plus 1 possible states, and in fact the engine cannot be at the cliff or nor at the goals, as this result in the end of the episode. And it remains on the positions of the first 3 zones of plus the bottom left cell. As also observation is simply the current position and code the as a flattened index. And it is the reverse of the environment here. Each time step incurs gets a -1 reverse and step into the cliff to and then we get the -100 reward. So this in the figure 1 considers the grid one. So this is a standard and discounted abstract test with a start test S and the goals test G, and the user actions causing movements up, down, right, and left. The reverse is -1 is all consistent, except though into the reason mask. The cliff remask cliff. So the stepping into the region incurs a reverse -1 is a cliff, and here with gray line, and send the engine instant back to start. And when to move on the cliff and back to the start, and we do we do the game, we test again. So let's talk about the methods that I use in my projects. The first one is the SASA's algorithm. The SASA algorithm is on policies temporal difference learning. Its basic transaction equation is the key values with respect to states an action is equal to the instant key value state action plus the lambda and we plot to alpha multiply with the reverse, the next reverse plus the gamma with the key values of the next state and action minus to the instant key values of the initial state and with action. So the first one we initialize the key values state value function with as state action value function. The state action value with s is corresponding to the s space and arbitrary release, and the q in the terminal state is 0. It is equal to 0. It means s q's s a equals 0. And for each episode, we do that initialize s, and we choose the action from the space, and using the policy derived from the queue. And for each step of episode, we take action, observe the reverse and the next state by observer, and we choose the next action from the news the space new state from the next state using the policy derived from the queue. There in the I don't know, is the algorithm is similarly the function similar to the similar function above, and then we do the s equal to next test, and the action we take to the next action, and we do the loop, and with the state is the terminal, we break the system. And next we talk about we using the Q-learning algorithm. It also the Q-learning, the one that breakthrough in reinforcement learning were developed in development of policy the temporal different controls algorithm. As known, the Q-learning is proposed in a ton of 1989. It defined by the Q values of state, the values of state action values. It means the Q values at state t is equal to Q values at state t minus 2 the alpha multiply with the next reverse, and we plot to the gamma multiply to max action with next the max corresponding to action with the next state, and with minus the key values at state t. First of all, we initialize the key value, so it's similar to the SASA, and for each step we do the initialize the state, and with each step we also choose the action from the state space, and using the policy driver from the queue, and take action A, observe the reverse and next state, and we use this algorithm and use this the function above, and then we take the next state is equal to the initial state. So it's the state here is the initial state. The temporal state is terminal, and it's the end. So then we break the loop, and now we break the engine. Here, by using the tool algorithm, we do experiment in the environment, the clip working environment. First of all, we testing parameter. We test parameters. In this project, we set more parameter using the tool algorithm, and this way to observe that what algorithm is are better and evaluate to algorithm easily. We have the 5 scenarios from 1 to 5, and we applied the alpha, Sarah, and Q learning in the Q learning, and Sarah is 0.5 and 0.1 respectively, and lambda and gamma is also. We both test both a one and but in the epsilon we test in the external world we test it is 0.1, and next 0.2, and channel 3 with 0.3, channel 4 is 0.4, and scenario 5 in with 0.5. So, and by using the more parameters to training or to in this engine training engine in this environment, we do the algorithm, and we also custom maps grid score larger than the initial environment with 6 rows and 15 columns. And as you can see in here, with Sarah, we average Sarah at the epsilon is 0 to 0.1. We see that the path is very the safe in move to the top and go straight and go to the trades and come to the world. But in the queuing, it's quite the optimal path, but it's very serious, and you can see here. But the path is shorter. We know that this is because the experiment does some random, and the result for each run are not exactly the same. But the path formation from start position to end position is the same, and here it comes we saw that. And as the true picture is on the previous slide, we saw that the queuing with generates with the optimal path, but it's very serious. In Sarah is generate and suggest the safer path, but the path is very long. So, but it's in the next picture here. So the Sarah has a higher average reward than Q-learning. This is in line with our expectation. Q-learning choose the optimal ways through the engine with the Q-learning. May have a maximum reward. It's very possible to get into the cliff with the epsilon grid strategy. That's also the also reason that the Q-learning cause it have some the sudden drops. Conversely, Sarah is gets a safer path and is not so likely get into the cliff. We also use average and observe the impacts on the performance with the different epsilon. In here, in the two picture for average reward from Q-learning and Sarah. So we would train the episode with different epsilon, and the raw with speaking one point is very 50 episode. As you can see, the finger so that's the reverse decrease. Then when the reverse decrease and when the epsilon increase. This is explainable if the epsilon increase, the possibility to getting the direct possibility to get into the direction of the cliffs increase. Once getting into the cliff, the reward will drop suddenly by -1, -100. That's also why the curve with the larger jog go with more amplitude. Here, also the more epsilon and the more epsilon, the less rewards. Before we do this project and we have some conclusion, Sasa is intent to set the path while Q-learning is prepared to choose the optimal path. And the fact to decide the random choice, the epsilon has a great impact on performance, and the larger epsilon makes the engine easier to go to the cliff, and making the reward decrease. The different epsilon will be get a different path, and especially when the epsilon is equal to 0, so it has the same path optimal as the Q-learning. And in addition, time execute into two algorithm is quite different. Time execute running on in Star algorithm is faster than Q-learning, so we know that the engine needs more time to think what way was to be optimal, similar to Q-learning, and what way is true and easy to choose the way safer, very easy. So thank you for seeing, and thank you for watching my presentation. So this is the end my presentation. Thank you so much.